it's time for the. So let's start. The speaker of this session is Alberto Castellano Mora. So he will tell us about the gravity no distance conjecture. Please start.
Okay, thank you. Good afternoon, everybody. Let me first start by thanking the organizers for putting this nice workshop together during these difficult times, and also for letting me speak here. Today, I will present some work done with my supervisor, Luis Ibanez, and also in collaboration with Ana Maria Font and Alvaro Rai. And it is based on a paper that we put on the archives about 4 months ago, which is called a gravity no distance conjecture. So, since this work is framed within the Swampland program, let me first review some of its main motivations and lines of vision. So, as you may probably have heard, the basic aim of the Swampland program is to try to answer the following question: whether every apparently consistent, semi-classically consistent effective field theory can or cannot be embedded into a consistent way into a theory of quantum gravity. And as we have learned during the past years, the generic answer turns out to be no, but in fact we can try to do better, and we can try to find those constraints which must be satisfied by effective field theory. In other words, what is the imprint of quantum gravity at low energies? And this has been done in terms of what are known the Swampland conjectures, such as the distance conjecture, the gravity conjecture, and so on and so forth. And the punchline of this conjecture is that basically this restrict the regime of validity of the effective field theory further than naively expected. And this is usually signaled by the appearance of infinite tower of light states whenever we try to go too far away from the original description. And this basically hints at some kind of universal behavior in several spatial points and moduli spaces and so on. And what we try to propose in our work is to sample a special direction, those in which the gravitino mass asymptotically vanishes. So what we basically propose is that whenever you have a theory of quantum gravity or a supersymmetric effective field theory with non-vanishing gravitino mass, and you can somehow make it to vanish asymptotically, there should appear an infinite tower of massless states, which is tied to the gravitino, following a power-like expression like the one you have here, and this is what we basically do, what we propose, and we will try to test. And I should also say that by the same time that we put this paper on the archives, there also appeared this other one, which basically proposes the same idea but with some complementary arguments. Also, that I encourage you to also check this on the archives. And as I should also say that this conjecture, as we will see, is nicely connected with other already existing ones. There's an outline. I'll first go through some introductory remarks about some of the Swampland conjectures which are most relevant for our work. Then I'll present the gravitino distance conjecture, and I'll try to relate it to the already existing constraints that we have in the Swampland program. And after that, I will present some evidence for the gravitino distance conjecture, both in type 2A or interval compactifications and also in F-theory flux compactifications. And finally, I will try to sketch some of the main phenomenological implications that it may have. So let me first start with the basics. So as you probably heard about, the Swampland distance conjecture is one of these conjectures, which basically tells that whenever you have a modular space left over in your effective field theory, and you start from some generic point P and try to go to another point Q, which is infinitely far away, measured with respect to the metric of the nonlinear sigma model in your modular space, which is basically given by the kinetic terms of your scalars. Then an infinite tower of states exponentially with exponentially decreasing mass appears, breaking down completely your effective field theory. And I should say that this Swampland conjecture has been very well tested during the past years and very well established with some really non-trivial checks. And it basically pinpoints at some kind of universal behavior near these infinite distance points, which should be behind this quantum gravity constraint. And I mean, one of the usual examples that comes into mind when trying to make sense of this conjecture is this causal claim theory. When we compactify our gravitational theory, maybe coupled to some matter on a circle, then we know that it appears a scalar field called the radium, which basically measures the physical radius of the circle compactification, which has the following metric. And you can see that there are two infinite distance points with respect to this metric. One, which is basically the compactification limit, in which it is the Caruso-Klein tower which fulfills the Sumland distance conjecture, but there's another infinite distance point in which the radius basically shrinks to zero size, and it is here where usually happens all this magic of this fact of the necessity of extended objects in these kind of arguments, in which because it is here the winding modes of the string theory which will make the conjecture to hold. I mean, there's analogously, a couple of years ago, it was also proposed this anti-de Sitter distance conjecture, which basically starting from some kind of generalization of the distance conjecture in order to apply it not only to scalar fields, but also to more complicated tensor fields. The authors proposed that if you actually apply this generalized distance conjecture to the metric itself, you can derive some kind of relation of this form, which basically tells you that whenever you have an effective field theory with a non-vanishing cosmological constant, and by tuning some parameters, such as, for example, fluxes, you can scan this family and approach the limit in which the cosmological constant goes to zero, then this should also be forbidden in quantum gravity. And you should see this by the appearance once again of an infinite tower of states which should be tied to the cosmological constant. And I should say that up to now, all the classical examples that we have are known to fulfill these conjectures in anti-de Sitter, but there have been some kind of refinements and strong versions of the conjecture, which basically try to restrict the ranges or put constraints on the ranges of the gamma parameter here, depending on whether we have some supersymmetry left over in our vacuum or not. But this has been quite controversial because not all of the examples seem to fulfill the strong versions of the conjecture. And so what is what we propose? Well, as I was telling you, what we propose that if we start from a supersymmetric theory with a non-vanishing gravitational mass, and we by changing some, well, I'll tell you, but by changing something, we can make it to asymptote the limit in which it basically penisses, then a tower of states should appear, which is becoming light, and which depends on the mass of the gravitino via this power-like expression. So let me first make a couple of few remarks about this. So in all explicit examples that we studied in the paper, there were two ways of approaching this limit. Either it could be that we have some modular space and flag directions in which we could freely move, such that we could make that we could approach this limit, and in this sense the conjecture was fulfilled in those cases, which is kind of reminiscent of the situation in the Sumland distance conjecture. Or either it could happen that all the parameters in the theory were fixed in terms of fluxes or whatever, and by tuning these discrete parameters, we could scan families of background in which this limit could be approached. And this more or less reminds us of the anti-de Sitter distance conjecture that I was talking about before. Or it could happen that we could have some kind of mixed situation between them both. But in any case, the framework that we basically used in the paper to test the conjecture is n=1 for the supergravity, in which the gravitational mass adopts the following form. It basically depends on the Kähler potential theory and also the superpotential. So one could ask, okay, but what is the point of adding another conjecture which it's seemingly unrelated to the already existing ones? And the fact is that this is not the case. I mean, this conjecture seems to be deeply connected to the ones that I was talking about. For example, in those cases in which we have a supersymmetric anti-de Sitter vacuum, it can be seen that the gravitational distance conjecture is completely equivalent to the anti-de Sitter distance conjecture. And why is that so? Well, in that cases, one can see that the cosmological constant is basically proportional to the square of the gravitational mass, so that making one of them vanishing already implies the other one. And by identifying both towers, the relevant towers in both conjectures, we can even relate the relevant exponents on both conjectures, which are simply related by a factor of 2 in these cases. But this, as I was saying, this only holds. This argument only works in the supersymmetric cases. But given that the anti-de Sitter distance conjecture is supposed to to hold also the non-supersymmetric ones. We also expect this that our conjecture, our gravity instance conjecture, it's also true in these cases, and in all the cases that we test in the paper, this is actually true. And but for me, the strongest argument, if you like, in these lines, or in the lines of the Swammland reasoning, is its connection with gravity conjecture. So the weak gravity conjecture is one of the oldest Swammland conjectures. It was proposed quite some time ago, and in its original form, it was formulated in two versions. One electric form, which basically states that in your spectrums there should be some subextremal particle in order to let extremal black holes to decay and not to run into problems similar to the ones that are usually used to motivate the no global symmetry conjecture in the Swammland program. And there was also another form of the conjecture called the magnetic one, which basically tells you that there's some UV quantum gravity cutoff, which depends on the gauge coupling, so that whenever we make this gauge coupling vanishing, and hence the gauge distribution freedoms are decoupled, and what we're left with is basically with the global part of the symmetry, this should be forbidden in quantum gravity. And I should say that this has been generalized to higher dimensional cases, to black brains from type 2 inspired supergravities, and also another kind of bounds between the tension of these objects and in relation with their charges has been derived in the same manner. So what does all this have to do with the gravity? Well, the thing is that in our n=1 4D supergravity effective field theory, as you remember, imagine that we have some kind of vacuum with a given gravitational mass in terms of the Calor potential and the superpotential. It is a fact that there's some BPS membrane, a codimension 2 object in your 4D theory, which basically has the attention proportional twice the value of this gravitational mass, and which can be seen to separate fluxless Minkowski vacuum to the one that you have derived, which gives you this configuration with this gravitational mass and so on. And this is usually made by some bound state between DP brains wrapped in some cycles, or NS5 brains. So we see that whenever we approach the limit in which the gravity goes to 0, the tension of such an object goes as well to 0, and by the BPS condition, the gauge coupling of the associated three forms, or the combination of three forms, also goes to 0. So that this no global symmetry conjecture applied to this generalized global symmetry should forbid this to happen. So what about the evidence that we present in the paper? So as I was telling you, in the book, most part of the paper, what we use is type 2A Calabi orientifold compactifications, in which some of the most relevant scales for us, such as the string scale, like the compactification scale, are seen to depend on the background expectation values of our 4-dimensional fields, such as the electron, the structure, and so on. We moreover focus on simple toroidal orbifold example with the following Calor potential, depending on the complex universal Calor structure, the universal complex structure, and the dilaton. And by turning some non-geometric and geometric fluxes, we can get some kind of superpotential, which basically sterilizes some of or all of our modeling, of the model in our theory. So in the paper, we discussed three different kind of examples. We have ADS vacua, both with and without metric fluxes. And in the case of with no metric fluxes, what we study is basically the DGKT and CPI family, which gives you some supersymmetric and non-supersymmetric solutions in which it can be seen that the gravitino conjecture is fulfilled with a value of delta slightly smaller than 1 of 7/9. And there are also some other anti-de Sitter vacua with metric fluxes, giving not supersymmetric as well as non-supersymmetric solutions with a delta parameter equals to 1, which basically tells you that the gravitino mass and the UV and the scale of the tower are around the same scale. We also discussed some Minkowski examples, and given that there's no known Minkowski backward with all the models stabilized. We study basically are node scale models in which supersymmetry is obviously broken. Otherwise, we wouldn't have any non-vanishing gravitational mass. And we here have two kind of situations. There's some vacuum in which the gravitational mass depends solely on a single unfixed modulus, so that we only have some leftover modular space, usually the complex structure in which the gravitational conjecture is fulfilled with a value of delta of 2/3. And it can happen that we have more than one node-scale directions, in which, in these cases, what one finds is a range for the values of delta rather than a specific value. But in any case, the important thing is that in all of them, we always have a lower bound for the delta parameter, which is the thing that has to happen in order to have a meaningful conjecture. Otherwise, we could decouple the infinite tower of states as much as we want. And we also discussed some DS runaway solutions, because in those cases, one can see very neatly how the gravitational mass is directly related to some kind of BPS members, as I was pointing out before. So what are the main general lessons that one can extract from all these examples? Well, first of all, one sees that the gravitational mass basically adopts the following form. It depends on the complex structure, modulus, and there's also some dependence on some flux bilinears contributing to the tuple cancellation condition. And this is not a coincidence. As is argued in the paper, one can motivate this from having our backward parametric control and the necessity of having some kind of cancellation between the positive terms and the negative terms of the scalar potential, given that the negative terms are given by basically the tension of the orientifold planes, which wrap special Lagrangian manifolds, so that they only depend on the complex structure. Second, we show that one can constrain further the range for the delta parameter by using quite general arguments, asking for the reliability of the effective field theory, in the sense that we should have our gravitational mass below the UV scales, and also by asking to have some perturbative control over the solution, meaning both 4D and 10D dilaton being small. So that we found a quite general value for Calabi-Yau threefold orientable compactification bounds for the delta, which is 1/3. And we also show that these singular limits are not only characterized by having some infinite tower of master states, but there also appear some strings and membranes which get tensionless in those limits. Those will be important in the end of by the end of the talk, because we will use them to constrain further these ranges in more general settings. So up to now, everything that I've discussed has been about the large volume point in type 2A and also with coupling limit. So the following question naturally arises. So can we be more general? Can we say more? Can we make general statements about whether this conjecture should apply to any infinite distance point in modular space, not only the common ones? And if so, can we say something quantitative about it? Can we put constraints on the delta parameter or anything like that? So this question was the original motivation for the next part of the paper. And so to accomplish that, what we used is the asymptotic Hodge theory, which is strong mathematical machinery which has been successfully used over the few past years in order to give more confidence on the Swammland distance conjecture, for example, with gravity conjecture. And but there's a problem, because as we saw in our explicit examples, in order to approach the limit in which the gravitino goes to 0, as well as having control over the solutions, both the color sector and the complex structure sector should have taken to be to the boundary. But this Hodge structure business is well adapted to attack only either the complex structure, for example, in type 2B, or the Calyx structure in type 2A. So that there was quite a problem in how to incorporate all this stuff while treating both sectors at the same time at infinite distance. So what we thought about is to uplift our solutions to a theory, because there the dilaton belongs also to the complex structure. And in this sense, we could recover not only, well, we could recover our previous solutions, or some of the previous solutions in both anti-de Sitter and Minkowski, and we could also make some more general statements about the validity of the conjecture and its ranges. So what are the lessons that one has to take home from here? Well, as we focused on the two-scalar field limit or codimension 2 loci in modular space, in which we only have the dilaton and the Kähler extractor. This wasn't, I mean, really an stringent condition, because most of our solutions could be recast within these lines, and by using some of the results that have been computed over the last years, we could establish that the gravitational distance conjecture was fulfilled those back where there were parametric control in both anti-de Sitter and Minkowski back, supersymmetric and non-supersymmetric. Second, we also used the unavoidable appearance of these tensionless membranes in connection with the gravity conjecture to put some constraints on the delta parameter. Whoops. So whenever you have a tensionless membrane, this is also accompanied by some tensionless actionated strings, because those objects form the basic gauge invariant objects in your effective field theory. And by using the approximations implied in the mixed structure, which I didn't tell you, but I really have time to go really into the details. You can, if you're interested, you can look at the very brief review which is presented on the paper. And by using this kind of approximations in all this business, one could obtain lower bounds for the delta parameter in both Calabi-Yau 3-fold or interfold compactification, or Calabi-Yau 3-fold compactifications and Calabi-Yau 4-fold compactification. Interestingly, these bounds were precisely matched precisely the values that we obtained by totally different means in the previous part by using other kind of arguments.
You have 3 minutes left.
Oh, okay. I'll wrap up. So we also tried to connect the gravitational distance conjecture with the Sumner distance conjecture. We did it both in the toroidal example and in using this generalization of the asymptotic Hodge theory. And we saw that in those cases in which you have some modular space left over and you could move freely in order to make this gravitational mass go to 0, those limits were at the infinite distance, and by identifying both towers we did with the anti-de Sitter distance conjecture, we could find another relationship between the both parameters, the parameters of both conjectures, and we found quite explicit relations between them, numeric relations between them, depending on whether we were in this toroidal setting on the more general setting of mixed structure. And interestingly, this by translating the bounds that we obtain for the delta parameter using this relation to the bounds on the alpha parameter in the distance conjecture, we found ranges which are in accord with those which are already known in the literature. And let me go quickly through the phenomenological implications. So as we know, the gravitational mass is an important parameter both for particle physics and cosmology. In Minkowski vacuum, we know that this gravitational mass measures the scale of supersymmetric breaking. And if you recall, the main lesson of all this business is that we cannot arbitrarily decouple the gravitational mass from the UV scale. So there's some kind of relationship like this between the gravitational mass and, for example, in the case in which it is the Kaluza-Klein tau, which is the leading one, we find this kind of relation. So what kind of implication could this have to particle physics? Well, one could ask oneself, at which scale do we expect to find the UV scales, the Tauer scale? So that using the most conservative delta parameter, or maybe the most decoupled parameter for the gravitational conjecture, one could envision the two settings. One in which the gravitational mass is around the LHC reach in order to accommodate the minimal supersymmetric external models of gravities and so on. And in that case, you find that the Kaluza-Klein tower should be at around 10 to the 8 GeVs. And something similar happens whenever you put your gravitational mass at 10 to the 10 GeV in order to make the scalar potential for the Higgs boson well behaved. In that case, the Kaluza-Klein scale should be a few orders of magnitude above. But in any case, what this tells you that the traditional deserted scenario in which you have the supersymmetry breaking scale around the LHC range, and then the compactification scale well above, close to the Planck scale is not allowed by this conjecture. And for cosmology, it implies some nice bounds having to do with the Hubble parameter. So as a quick summary, we've studied this kind of limit in which the gravitational mass goes to 0. We've seen that this selects particular directions in which a tower of states of light states develops tied to this gravitino. But we also found some leading towers of coming from tension strings and membranes. We found a direct relation with the gravity conjecture, which supports this constraint, this idea, basically by telling us that in this limit, we should recover some free-form global symmetry, and this should be forbidden in quantum gravity. We also relate our conjecture to both the anti-de Sitter distance conjecture and the Swammerdam distance conjecture by two means: by using type 2 Calabi orientifold compactifications, and also by a more generic flux F-theory flux compactifications. And we obtained some nice bounds using the mathematical machinery of mixed hot structures for the delta parameter, which match with the explicit ones that we found in our example. And for the phenomenological part, we saw that this has nice implications both for particle physics and cosmology. And I should also say that there has been another recent paper, which points that even though the models they studied in eight dimensions, most of them fulfill the gravitino conjecture. They think that there could be some Susy breaking backward, but with the close, some Susy breaking backward in the brains, which could give a counterexample for the conjecture. So that's all. Thank you for listening.
Okay. Thank you for the nice talk. Now it's open for the question and comment. Is there anything? If you have something, you can just unmute yourself and speak up. So Pablo, you have a question? You turned on your video.
Hi, can you hear me?
Yeah.
Oh, hi. Thanks for the nice talk. Can you comment on the relation with KKLT? Because is there a tension, because the ADS distance conjecture seems to be in tension with KKLT. So is the same for your conjecture as well?
Yes, in the paper we don't use KKLT as an example of the conjecture. For example, the other people, the Criviori et al., use it as an example for the conjecture, because, well, they say that there has been some recent paper of Blumenhagen, I think, in which they say that this in the previous step, before putting the anti-D brains in the warp throat, there should appear another leading KK tower, which with a logarithmic dependence such that the anti-de Sitter distance conjecture should hold, but with some logarithmic corrections coming from the quantum corrections, so that in this spirit, the thing is that we don't comment on KKLT because it's not an actual now example rigor. But if you take this proposal of the new KK scale having to do with the warp throat, as long as it's true, it should work. But
so you're saying that this tower that Blumenhagen et al. Mentioned that arises at the warp throat, it would mean that that is the tower related to the gravitino conjecture.
Yeah,
distance conjecture.
The previous step, if that tower is the one that makes the anti-de Sitter distance conjecture holds, then immediately the gravitino distance conjecture holds. And well, the step in which you add the anti-de Sitter, the anti-D3 brains, if that contributes to this change or not, it's something that I'm not sure, but as long as this,
right.
So
I think as long as the ADS distance conjecture would be satisfied, the anti-brain uplift probably wouldn't change that. These, okay, right. Thank you.
Any other question or comment? Yeah, I think it's almost time. So let's thank Alberto again. Thank you very much. And the next session will be a plenary talk. So you can use this breakout room for the discussion until 4:40.